നമ്മൾ കാണാൻ പോകുന്ന ടോപ്പിക് ഐഗൺ വാല്യൂസ് ആൻഡ് ഐഗൺ വെക്ടേഴ്സ്. So suppose A is a square matrix of order n. Then if you find determinant A minus lambda I equal to 0, this will be an nth degree equation in lambda. For example, suppose A is equal to matrix 1 minus 2 minus 5 4. Then we take I as an identity matrix of the same order, so that lambda I is equal to lambda 0 0 lambda. So A minus lambda I equal to matrix 1 minus lambda minus 2 minus 5 4 minus lambda. So if you find determinant A minus lambda I, this will be equal to 1 minus lambda into 4 minus lambda minus 10, which is equal to lambda square minus 5 lambda minus 6. So if A is a 2 by 2 matrix, when you find determinant A minus lambda I, what you get is a polynomial of degree 2 in lambda. Likewise, if A is an n by n matrix, if you find determinant A minus lambda I, you will get a polynomial of degree n in lambda. So equated to 0, this gives an equation of degree n in lambda. And we know an nth degree equation has n square roots. So if lambda 1, lambda 2, etc., lambda n are the square roots of this equation, we call this as eigenvalues. Now, determinant A minus lambda I equal to 0, this equation is called characteristic equation. And thus the eigenvalues are the roots of the characteristic equation. So it is called characteristic roots or latent roots. So eigenvalues are obtained like this. You find the characteristic equation of the matrix, solve the characteristic equation, the roots are called the eigenvalues. Now the collection of all eigenvalues, ഇതിൽ repetition ഉണ്ടെങ്കിൽ ഒഴിവാക്കണം, lambda 1, lambda 2, etc., lambda n. This set is called the spectrum. So spectrum of a matrix is the set of all distinct eigenvalues of that matrix. Now if you find the eigenvector corresponding to the eigenvalue lambda, we define the eigenvector like this. So suppose A has eigenvalues lambda 1, lambda 2, etc., lambda n. Now eigenvector corresponding to the eigenvalue lambda, it is obtained by, or say lambda I, where I varies from 1 to n. It is obtained as the solution of the homogeneous system of linear equations A minus lambda I into x is equal to 0. So if A is n by n, x is a column containing n variables, x1, x2, etc., xn. And the non-trivial solution of this system is called the eigenvalue. So obviously x is equal to 0 is a solution, but we don't take it as eigenvector. The non-trivial solution of this system is called the eigenvector corresponding to the eigenvalue lambda I. For example, for the matrix we have considered before this, is that matrix? So the matrix we have considered was 1 minus 2 minus 5, 4. And we obtained the characteristic equation as lambda square minus 5 lambda plus 6 equal to 0. So we find values of lambda for this equation, or we solve this equation, and this can be written as lambda plus 1 into lambda minus 6 equal to 0. So the values of lambda are minus 1 and 6. Now if you want to find the eigenvector corresponding to lambda equal to minus 1, we solve the system A minus 1 into minus 1 into I into x equal to 0. So here we know A minus lambda I is the matrix. If this is A minus lambda I is the matrix obtained by subtracting lambda from the diagonal. So 1 minus lambda, minus 2, minus 5, 4 minus lambda. What we do is we replace this lambda by minus 1. That is A minus 1 into I. So we get the matrix 2, minus 2, minus 5, 5 into x is the column x1, x2 equal to 0, 0. Now if you reduce this matrix, effectively if you look at this expression, you can see there are only only one equation, which is x1 minus x2 equal to 0. Or if you reduce this, you will get rank equal to 1 and minus r equal to 1. So we give arbitrary value to one of the variables, say x2. If x2 equal to a, then from the equation, our equation is x1 minus x2 equal to 0. So then x1 is also equal to a. So we can write x is equal to a, where a is not equal to 0. We restrict a to be non-zero because if a is 0, we get the trivial solution 0, 0. And we don't accept that as an eigenvector. We seek for non-trivial solution of the system. So x is equal to a, where a is non-zero. And hence we have the eigenvector corresponding to the eigenvalue lambda equal to minus 1. Now this defines a direction, that is, you can take an eigenvector 1 minus 1. So this 1 minus 1 corresponds to x is equal to x is equal to minus y. So 1 minus 1 corresponds to this vector. 1 minus 1 corresponds to this vector. Okay. 1 minus 1. This is minus 1 plus 1. And hence any vector in this direction will be a constant multiple of this. And that is expressed as AA. So any vector in this direction will be an eigenvector corresponding to lambda equal to minus 1. Now we take the next eigenvalue, that is lambda equal to lambda equal to 6. So when you subtract, When you substitute it in the matrix, our matrix is A minus lambda I equal to 1 minus lambda minus 2 minus 5 4 minus lambda. So when lambda equal to minus 6, we try to solve the system A minus 6i into x equal to 0. So we get the system as minus 5 minus 2 minus 5 minus 2 into x1 x2 equal to 0 0. So we have just one equation, 5x1 plus 2x2 equal to 0. So if x2 equal to a, x1 equal to minus 2a by 5. So the eigenvector for lambda equal to 6 is x is equal to x1 is minus 2a by 5 and x2 is a. So if I give a the value 5, I can take one of the eigenvector as minus 2 5. Okay. So this define another vector in plane minus 2 5. So the first eigenvector we have taken is 1 minus 1 and the second one is minus 2 5. Obviously minus 2 5 is not a constant multiple of 1 minus 1, hence they are independent, or in other words, if you write 1 minus 1 minus 2 5, rank is equal to 2. So they are two independent vectors in R2 and we know the dimension of R2 is 2. So if you take this set 1 minus 1 minus 2 5. Now as I said before, any eigenvector corresponding to lambda equal to 6 will be a vector in the same direction, a constant multiple of minus 2 5. So if you take these two vectors, as the rank is 2, they are linearly independent. And as the dimension of R2 is 2, this will form a basis of R2. Any set of two linearly independent vectors will make a basis of R2. So this is a basis of R2 and we call this as eigenbasis, a basis consisting of eigenvectors. So if A is a 2 by 2 matrix, if you pick the eigenvectors corresponding to distinct eigenvalues, you can form a basis of the basis of R2, and that is called an eigenbasis. Now, if the matrix is a symmetric matrix, this will be an orthogonal basis. For example, suppose you consider A is equal to matrix 1, 2, 2, 4. Then characteristic equation is determinant A minus lambda I equal to 0. That is determinant 1 minus lambda 2, 2, 4 minus lambda. This is equal to 0. So we have 1 minus lambda into 4 minus lambda minus 4 equal to 0. That is lambda square minus 5 lambda plus 4 and minus 4 cancels equal to 0. So lambda into lambda minus 5 equal to 0. So lambda equal to 0 and 5. So 0 can be an eigenvector, and obviously if 0 is an eigenvector, determinant A will be equal to 0 because we find the eigenvector such that determinant A minus lambda is equal to 0. So if lambda happens to be 0, that means determinant A is 0. So we can we can find the eigenvector for lambda equal to 0. So substituting lambda as 0, we get 1, 2, 2, 4 into x1, x2 equal to 0, 0. Obviously, the second vector is 2 times the first vector, so the rank is equal to 1. And we have just one equation, x1 plus 2x2 equal to 0. So if x2 equal to a, then x1 equal to minus 2a. So we get the eigenvector as minus 2a, where a is not equal to 0. Now for lambda equal to 5, we have the system minus 4, 2, 2, minus 1 into x1, x2 equal to 0, 0. So we get this as just one equation. The first equation is minus 2 into second equation. So we have the equation 2x1 minus x2 equal to 0. I am not going to repeat everything. So if x2 equal to a, or if x1 equal to a, x2 equal to 2a. So we get the eigenvector as a, 2a. Now look at these two directions. If you give a the value 1, we get the first vector as minus 2, 1. Right? This vector. So minus 2, 1 എന്ന് പറയുന്ന ഡയറക്ഷനിലായിരിക്കും ആദ്യത്തെ വെക്ടർ minus 2, 1. ഓക്കെ, ഇതാണ് നമുക്ക് കിട്ടുന്ന ആദ്യത്തെ ഡയറക്ഷൻ. Then the next vector is in 1, 2. X is 1, y is 2. ഇതാണ് നെക്സ്റ്റ് ഡയറക്ഷൻ വരുന്നത്. This is minus 2, 1 and 1, 2. Okay, and if you take the dot product, let us name x1 as the vector minus 2, 1, x2 as the vector 1, 2. You can see x1 dot x2 equal to 0. Or these vectors are orthogonal vectors. So if you write a basis using these vectors, that will be an orthogonal basis. The set minus 1, minus 2, 1, 1, 2 is an orthogonal basis of R2. So if A is a symmetric matrix, from A you can get an eigenbasis which is an orthogonal basis of R2. അപ്പോൾ 2 by 2 ആണെങ്കിൽ R2ന്റെ nth order ആണെന്ന് വെച്ച് കഴിഞ്ഞാൽ you will get a basis for Rn from the set of eigenvectors called the eigenbasis.